Okay. Hi, everyone. Hi. So, is there any question about the previous session before we start? No? Okay, so everything was crystal clear? Okay. Okay, so as I said again, feel free to interrupt me whenever you have any question. You don't need to raise hand, just say your words. And okay, so last session we talked about some preliminaries on sets and functions and convexity and these things. And at the end of the session, I remember we talked about the dimensionality of derivative. So we started with the fact that what is the definition of derivative, and from that we tried to understand how to determine the dimensionality of derivative. So let's review it briefly and then we will continue. So we said that derivative of something with respect to another thing means that change or tweak that other thing and see how much does it impact that thing, right? Some derivative of Benjamin with respect to desk is what? Change the desk and see how much I change, right? So this is the derivative. And now let's see the cases. The derivative of a scalar with respect to another scalar. Assume derivative of A with respect to B, where A and B are both scalars. And what is it? So what you tweak B and see how much it impacts A, right? How many changes do we have? We have one change, and that therefore the derivative is a scalar also. Derivative of a scalar with respect to a vector. So let's change the elements of the vector one by one. So when I change or tweak the one element, I let the other elements be fixed, right? And then how I see how much each change changes that scalar. So derivative of a scalar with respect to a vector becomes a vector. Derivative of a scalar with respect to matrix with the same analysis becomes a matrix. Derivative of a vector with respect to a scalar becomes a vector. Derivative of a vector with respect to vector becomes a matrix. Derivative of vector with respect to matrix becomes a rank 3 tensor. Derivative of a matrix with respect to matrix becomes a rank 4 tensor. What do I mean by rank 3 tensor? It's just a matrix with height, right? So width, height. How do we say? It's like becomes like a cube. Okay. So by the way, note that we have several definitions for tensor in mathematics here. I mean just generalized matrices to higher dimensions. Okay. So yeah, I think now here I'm talking about the dimensionalities, and I think I already explained these to you. Just you should note that when we say derivative of a scalar with respect to a vector with d dimensions, the derivative also becomes d-dimensional vector, right? So, and one of you guys might say derivative of a scalar with respect to a d-dimensional vector. Assume the vector is column vector, so it's d by 1. Is the derivative 1 by d or d by 1? Some of you guys might be very picky and ask such questions. I will say doesn't matter. Whatever convention you choose, you should stick to that until the end. So when you are saying that the derivative becomes 1 by d, it means that you have kind of transposed the derivatives. Therefore, you should transpose everything. You should transpose everything. And you will know what to transpose. Why? Because if you don't transpose, if you transpose the derivative and don't transpose the other elements in your mathematical expression, it will be nonsense in terms of matrix multiplication. So matrix multiplication of A times B, for example. Assume this is 3 by 2. This can be 2 by anything, right? But these 2's should match. If they don't match, it's nonsense mathematically. Therefore, as I said, you will find out, you will understand by first glance that when you transpose the derivative, you need to transpose other things. Otherwise, you can't multiply mathematically the matrices, I mean, and the vectors also. Is it clear? All right. Okay. Now gradient, Jacobian, and Hessian. So, what is gradient? Don't worry about that. It's just the naming, I think, is not important. The only thing which is important is mathematics behind them. The naming, we can call it Jack, whatever. So, in simple words, you can see that derivative, first order derivative, gradient, and Jacobian are the same thing. But there's some slight difference between them. And what is that? Usually, when the derivative becomes a vector or a matrix, we call it, usually when it becomes a vector especially, we call it gradient. So when the function, assume you are taking the derivative of a scalar function. What do I mean by a scalar function? The output of function is a scalar. And assume the input of the function is a vector or matrix, like this case. Function f gets a vector rd and outputs r. So it maps x to f of x. By the way, you know the meaning of map, right? It's a mathematical concept. So you can say that all functions are maps, but not all maps are functions, right? You know, I think the definition of function, for the same input, you shouldn't get multiple outputs. You should always get one output. That's the definition of function. So you can see function is a map which maps only to one thing for the same input, right? So here we usually denote map by this in mathematics. And what do I mean by this? So it means that from which domain do I map to which domain? So I get RD I already defined in the previous session. It's a d-dimensional Euclidean space, real numbers, to scalar, real or scalar. And why do we work with real? Because we usually we work with real numbers unless we are doing something complicated such as quantum mechanics and these things, right? Okay. So as I said, let's consider a function which gets a vector and outputs a scalar. So it's a scalar function. Then the derivative becomes, according to our analysis that I said, what is a derivative? It's a vector, right? It's a vector, d-dimensional vector. And we can denote it by this. So this, and also by this. So different notations. What is this, by the way? What is this notation? Always ask for notations. So if you don't understand anything, you should understand everything, okay? Don't miss anything. So what is this notation? It's just defined. In computer science, this is defined. So in different fields of science, we have different notations for define. So for example, mathematicians usually use this for define, right? I don't know if you have seen these in the papers, but computer science people usually use this for define, but it's a bit confusing. Why? Because also computer scientists use this for assign. So they use this sometimes for define, sometimes for assign. So it depends on where they are using that. Doesn't matter. Maybe the reason is that you can see assign as a kind of define too. Because when you say assign 3 to x, you can say I define x to be 3. Doesn't matter. So here, as I said, gradient is a vector, therefore I call it gradient. Sometimes, maybe you're taking derivative of a scalar with respect to a matrix, that gradient becomes a matrix. That's fine, you can also call that gradient. I myself had a paper where the gradient was a matrix. But you should be careful, that's a matrix in your calculations. Doesn't matter. Okay, so gradient I think is clear now. Let's move on to the second derivative. Second derivative is when the second derivative becomes a matrix, we usually call it Hessian. Okay. So when does this happen? When does the Hessian become a matrix? When the function, whatever we are taking derivative of, is a scalar, for example, and the variable is a vector. But when you take derivative twice, it becomes a matrix. Why? Let's see and analyze. First order derivative of a scalar with respect to a vector becomes a vector, d-dimensional vector. Then I need to take derivative again. This time I should take derivative of a vector with respect to vector again. D-dimensional vector with respect to d-dimensional vector. Therefore, the second order derivative becomes a d by d matrix, and that actually a square matrix. Why? Did you understand what I'm saying? Derivative of f with respect to x, it becomes a vector. I need to take I call it g. Now I need to take derivative of g with respect to x again for the second derivative, second order derivative, right? Then this g is d-dimensional. This x is also d-dimensional. According to our analysis, it becomes a matrix, d by d dimensional matrix. Therefore, Hessian is d by d. You see that? And we can denote it in different ways. Hessian. By the way, in the literature of optimization, pure optimization, I mean, if you go to optimization departments, the people who work with second order derivative, they usually denote in their papers, they denote Hessian by B and Hessian inverse by H. You might find it confusing. I myself found it confusing because H is the start of Hessian, right? But they use that for Hessian inverse. But they use B for Hessian. Again, naming is not important. You can call it whatever you want. And the Hessian matrix is symmetric. If the function is convex, then the Hessian matrix is positive semi-definite. Why? Because when it is convex, it's facing up. And I told you that the second order derivative in a scalar, when it is a scalar, it should be positive for the function to face up and negative for the function to face down. However, when we have multiple dimensions, then the second order derivative becomes a matrix. Then in this case, for the function to face up, it should be positive semi-definite. For the function to face down, it should be negative semi-definite. What is positive semi-definite? It means that its eigenvalues are non-negative. What is negative semi-definite? Its eigenvalues are non-positive. Clear? By the way, as I said, I don't want to be the sole speaker. Let it be discussion-based. Yeah. The symmetric. Okay, ask me. So why didn't you ask me? So yeah, ask me whenever you have any question. So symmetric means that it is equal to its transpose. So, for example, assume Bij denotes the ith row and jth column of B. If it is symmetric, it means that Bij equals Bji. So if you mirror it from the main diagonal of the matrix, it becomes the same, right? So it is equal to its transpose. Okay, Jacobian. Jacobian is usually when the derivative, the first order derivative becomes a matrix, we call it Jacobian. So when the first order derivative was a vector, we called it gradient. When the first order derivative becomes a matrix, we call it usually Jacobian. So when does that happen? When the function, assume, gets a vector and outputs a vector. But the input vector and output vector do not necessarily need to have the same dimensions, right? So assume D1 dimensional as input, D2 dimensional as output. Then we will have a matrix. Do you agree? Of course, according to our analysis, the derivative of a vector with respect to another vector becomes a matrix. And what are the elements? It will be derivative of first order. Derivative of F1. What is F1? So here the output, as I said, is D2 dimensional, right? Let me call this F1, F2 until FD2. What is this? X1 until XD1. Do you agree? So I can take derivative of each of the elements of f with respect to each of the elements of x. Exactly this is what I have done. In other words, you can see it as a partial derivative, right? Because f has several elements. Also, x has several elements. So each of these derivatives is a partial derivative. It becomes d1 rows with d2 columns. Again, as I said, if you consider it to be d2 by d1, then you have to transpose everything in your mathematical expression. So this is called Jacobian. Okay. We defined gradient Jacobian and Hessian that you see a lot in optimization. Yeah. Let me think. Which one? The top right one. You mean this, right? Yeah, I think it's a typo. Yeah, right. Thank you very much. Yeah, thank you. So yeah, the first row here is the derivatives of the elements of the f with respect to x1. The first column here is the derivative of f1 with respect to all of the elements of x, right? Okay. By the way, if I make any mistake, let me know. I also make mistakes. Like here. Thank you very much for letting me know. So consider the function. Now let's talk about general optimization problem, right? So consider the function f from Rd to R, where it maps x to f of x. Let the domain of the function be D. I mean, where the x can be defined for f. X belongs to D, and x is D-dimensional, right? Then on the unconstrained optimization, in this case, minimization, you can consider it as maximization as well. Doesn't matter. Unconstrained minimization of a cost function f is this: minimize f of x with respect to x. I put the optimization variable here, right? Where x is the optimization variable, and the function f is called the objective function or cost function. Why do I call it cost function? Because I want to minimize it. If I wanted to maximize it, I probably would call it either objective function again or fitness function or whatever, benefit function, whatever you call it. Okay, now constraint optimization. Constraint optimization problem is where we want to minimize or maximize the function f while satisfying several inequality constraints and several equality constraints. What do you mean by inequality constraints? Assume some expression of the x less than or equal to something, or greater than or equal to something. These are inequality, right? Equality constraints, what do I mean? Some function of f, some expression of x, equals something, right? So we can assume M1 inequality constraints and M2 equality constraints. And each of these can be a function of x, right? Some function, whatever. X plus tangent of x over the square root of x, doesn't matter, right? Now, this is also the cost. Can you tell me why do I have, so several questions arise here. Why do I have less than or equal to for all of the inequality constraints? Sometimes you might have greater than or equal to, right? Why have I put less than or equal to for all of the inequality constraints? Exactly. Whenever you have greater than or equal to, you can simply convert it to less than or equal to by multiplying the size by -1. Assume this is the case. Multiply the sides by -1, you will have this. Then, as I said, the naming is not important. You define this minus yix as another yix, as g of x. You can define the functions, right? So as I said, what do I mean by this? By the way, you understand this, right? What do I mean? For all I from 1 to n1. So this is condensed notation. this is actually like this: y1x less than or equal to 0, y2x less than or equal to 0 until ym1x less than or equal to 0. Also, this is condensed version for this: h1x equals 0 until hm2x equals 0. So I have m2 in equality constraints and m1 inequality constraints. For each of these inequality constraints, if it is greater than or equal to 0, simply multiply the size by -1, right? The second question which arises: why have I put 0 on the right-hand side of both equality and inequality constraints? It can be anything, right? Why have I put 0? Yeah, you can, exactly. So you can answer in this way, in an organized way. So if the right-hand side has some x in it, simply bring it to the left-hand side. Okay. However, if the right-hand side has some constant, again, bring it to the left-hand side by subtracting the sides from that constant, exactly as he said, right? So assume, example, assume here yix is less than or equal to c, simply bring c to the other side. Yix minus c is less than or equal to 0. Now I define this to be another yix or g of x. Naming is not important, right? Did you get it? As a result, this is the general form of constraint optimization problem. Okay. So example is this: minimize this cost x1. Here in this example, my x is a two-dimensional vector, so it's x1 and x2 transpose. Why do I have transpose here? Because I usually consider my vectors to be column vectors by convention, right? And here you can write it as minimize the vector x, bold x, or minimize different kinds of notations, x1 and x2. Doesn't matter, right? Then I have, this is the cost, but I have several constraints. So I can bring this 5 to the other side here. Also, I have greater than or equal to, I can multiply the sides by -1. Therefore, I will get this. I multiplied the sides by -1, and then I moved 3 to the other side, right? Also, this is the equality constraint. So here, in this case, m1 is 2 and m2 is 1, right? I have 2 inequality constraints and 1 equality constraint. Agreed? Okay. Now, feasible point. The point x for the optimization problem. So this is the general case constraint optimization problem, right? I can say this is the general form of optimization, because optimization is either unconstrained or constrained. And unconstrained optimization, you can see it as a special case of constraint optimization, right? Because unconstrained optimization problem doesn't have any constraints. So m1 is 0, m2 is 0. Then, so this is a general form of optimization. Now, in this, I want to define something named feasible point. Feasible point is a point which satisfies all of the constraints, equality constraints and inequality constraints. And then also, it is in the domain of the cost function as well, right? So it should satisfy all of these constraints. Also, it is allowed to be entered to the function f, right? And what do we mean by, so of course our solution will be, do you agree that our solution to the optimization problem should be feasible? Do you agree with that? Must be feasible.
Is that enough considered another constraint?
Yes, exactly. So maybe you can say that X belonging to the domain of F is kind of another constraint. Yes, you can say that. Yeah. You mean this? You can kind of insert it to be one of these or several of these. You don't agree with me? I can tell you. For example, the square root of f of x is the square root of x. X should be non-negative, am I right? Then you can say x is less greater than or equal to 0, so it is one of these. An example. But let's make it more complicated. Assume your D is very complicated, such as this. The worst case scenario. Then what happens? What can I do? I can simply make it a lot of constraints. With a lot, assume with a lot of this is one way to handle it. There are several ways. Then what does it mean? This says it should be here. This says it should be here. This is, it should be here. This here. Each of these is one inequality constraint. A simpler case for you to understand is this. Assume D is like this triangle. Then it can be defined by 3 inequality constraints. This, and this. This one says it should be here. This one says it should be here. This one says it should be here. So all together, they say that it should be inside the triangle. After that, can you explain better? So is it sort of like you already have a function? Yes. And then you have the constraints that limit the like the surface space of the function. Yes. Yes, exactly. So X cannot be wherever it wants to be. There are some restrictions or some constraints for X, right? Usually we need sometimes to constraint. Why? Can you tell me? Let me tell you an example. Assume I want to maximize this function. Assume f is like this. What is the maximization? What is argmax and what is max? Argmax and max, we defined it in the last session, right? What is max? Please tell me. What is max? It's going up and up and up. What is max? Infinity. What is argmax? In which x does it become infinite? It has 2 argmax, right? Infinite and minus infinite. But it's nonsense. We usually don't want to find infinite solutions, right? Therefore, we constrain it. We constrain it and say x must be between -5 and 5, for example. Then when you constrain it, it can't go until infinite. Then the solution will be argmax will be 5 and -5. So it is x squared. Therefore, the max will be 25. Right? Yeah, of course, you can do minimization on this too. Then the minimization will be 0. I'm saying that assume. So in this case, that in some problems, that your solution, if you don't constrain, the solution becomes infinite. They call it ill-posed or ill-defined optimization problem. Ill-posed, ill-defined, different names. Okay. Then they say for this to not to be ill-posed, let's add some constraints. Right? In machine learning, actually, they do that a lot. They want to optimize something. It is ill-posed. They add a constraint. Okay. So here, we already talked about now. Again, the solution to the optimization problem must be feasible, of course, and also at the same time it should minimize the cost function. So the solution simply is this: which point in the feasibility set, the set that the feasible points exist, or in the set of constraints, which point of these minimizes the cost function? Did you understand? Consider this. Assume this is the cost. This round. And what do I mean by each line? On each line, the cost function is the same. Function value is the same. So when I draw this, what do I mean? It's a bowl. Assume it's a bowl, right? The end of the bowl is here. And this bowl, just from this figure, we can't find out whether the bowl is going down or up, right? We just know that it's a bowl. Assume this bowl is going up. So its minimum is here, right? Then I have some feasibility set. Assume I have here, in this case, I have 1, 2, 3, 4, 5, right? 5 inequality constraints. Then what will be my solution? Here, because 0 is in the feasibility set. But what if, for example, this was the bowl and my constraint was this, the right-hand side? Then the solution would be probably here, right? Here, the cost is minimized. Did you get it? Here, I showed you some examples for the... Do I have an example for... Yeah, okay, let me give you an example for equality constraints. So here, let me add a page. Okay. Assume this is my cost. Assume I have two inequality constraints. One of them is like this. By the way, you understand when I draw a line, what do I mean? Here, for example, I have x1 and x2, right? In my visualization. And the third dimension, which I'm looking from above, is the cost value, right? So my face is here. I'm looking at the cost. And the plane is x1 and x2, right? When I draw this, I actually mean it's a plane in this case. It's a plane. If I only have one x, so if a scale x is a scalar, the line becomes actually a line. When x is in R2, yeah, let me think. No. Yeah, here also the line here becomes a dot, I guess. Yes, so here, what do I mean? Assume this is x. Then whether I'm the left-hand side of the dot or the right-hand side of the dot. When I'm in R2, the line is actually a line. So what do I mean like this? Whether I'm in the right-hand side of the line or the left-hand side of the line. When I'm in R3, what does it mean? The line is actually a plane. Which side of the plane I am? When it is in R4, R5, it's a hyperplane. Don't be scared by the name hyper. Whenever mathematicians, whenever they want to say that it's in higher dimensions and we can't visualize it, we need to imagine it, they call it hyper. Right? Hyperplane, hypercube, hypersphere. Right? Hypersphere is a sphere in higher dimensions. So here I have, in general, it's a hyperplane. And then here in this case, it's a line. So assume I have two constraints like this and this. And one equality constraint. So two inequality constraints and one equality constraint like this. My equality constraint says that I have to be on the line or on the hyperplane. So basically, what is the intersection of all of these constraints? Can you tell me? So I have to be here, also here, down there, also on the line. So it's basically here that I'm making it bold. On the line, inside the region satisfied by the inequality constraint. So this is the, now on the points in this is the feasibility set. I have to search for my solution. Does you understand? Okay. Now, also another way to define the constraints is just a set. So I can say that my feasibility set is S, right? Whatever you call it, right? And my X must be inside S. So my X should satisfy the feasibility constraints. Should be or should lie in the feasibility set. Clear? Now, an important thing. How to convert a constraint optimization problem to an unconstrained optimization problem. Why do we need that? Because usually in meta-heuristic optimization, that we'll see, we usually work with unconstrained optimization. Right? Now, if we have a constraint optimization, let's convert it to an unconstrained optimization problem and then use meta-heuristic optimization to solve it. So, okay. Consider this constraint optimization problem. Minimize f of x subject to g of x is less than or equal to 0. This is a constraint hard penalty. So this is constraint. And why do I call it hard penalty? Because you can see the constraint as a penalty, and if it is not satisfied, it kills the optimization problem. It actually kills it. Right? So if my solution doesn't satisfy the feasibility, the constraints, it's done. It's useless. Throw it away. Right? So it's hard penalty. Now I can say, okay, I want to minimize f of x, right? At the same time, I want g of x to be small. Why? Because for this to be satisfied, g of x less than or equal to 0, g of x must be small, right? It shouldn't be 100, it shouldn't be 1000, it should be small. In other words, I can kind of say, let's minimize g of x also, right? When I minimize g of x, it kind of does what I want. G of x is pushed towards 0 or negative values, right? Therefore, now let's combine these two together. The simplest way to combine two things is what? Linear combination, right? I want to combine me and you. I say half of point 1 of me, 0.9 of you. Half of me, half of you. Do you understand what I'm saying? So linear combination is the easiest way to combine two different things. So let's do that. F of x plus some weight times g of x. So I weight them. And this lambda is a weight. It says how much should I care for minimization of g of x compared to minimization of f of x. Right? The larger the lambda, what happens? The larger the lambda, what happens? What? The larger the lambda, I agree, the bigger the cost, but what does it do? What is its impact? So the larger the lambda, it says the more I should care about minimization of g of x. If lambda is close to infinity, what does it mean? Ignore f of x completely. If lambda is 0, what does it mean? It means that ignore g of x. So lambda is a greater than or equal to 0, or greater than 0, you can say. Right? We usually call this lambda regularization parameter. Regularization parameter. What do we call this? We call it regularized cost. Have you heard of regularization in machine learning? They're doing one way to do regularization. Almost you can see all of the regularization techniques in machine learning as a minimization of a regularized cost function. An example is weight decay in neural networks. So you have regularized cost. Okay. This is a soft penalty. Why? Because here g of x must be less than or equal to 0. It can't be 1.11001. Here it can be. It can be small, but it can be 0.001. Do you agree? Therefore, this is a soft penalty. It doesn't kill the optimization problem, right? An example for you to understand soft penalty versus hard penalty in real world is this. Again, what do I say? This is an example, don't take it controversial. So assume really. I only say these things because these make you understand very well. So I say, I want to become a great scientist. Otherwise, if I don't become a great scientist, I will kill myself. Okay. Assume this is hard penalty. Then another case, I want to become a great scientist. If I can't become a great scientist, I will not buy myself a pizza. This is hard penalty versus soft penalty. Did you get it? In both cases, I'm penalizing myself. I know science is very fun. See, so in both cases, I'm penalizing myself. But in one of them, it is hard. When I say hard, it's done. If I kill, it's nothing else, right? So now you will see why do I use the word kill? Because killing in mathematics, you will see that. Okay, now listen, please. So, guys, listen. So now I have assume there's another way. There's another way to convert. So by the way, one more thing to tell you about this. There's a lot of things that you can talk about just with this simple equation. Have you heard of Lagrangian? Lagrangian is also kind of in the same format. So you have regularized cost. You can interpret Lagrangian as a regularized cost. So what do I mean? Let me add a page. Minimize f of x with respect to x subject to x, I don't know, y of x. Assume I have only one, y1 of x is less than or equal to 0, y2 of x is less than or equal to 0, and maybe h of x is equal 0. So the Lagrangian is simply this. F of x plus lambda 1, y1 x plus lambda 2, y2 x plus gamma, nu, whatever you call it, nu h of x equals 0. No, not equals 0. This. What is this? In mathematics, they call it, in mathematics of optimization, they call it Lagrangian. Named after Lagrange, was a great mathematician. Okay. Now I think you can understand Lagrangian very well. So what does Lagrangian do? Lagrangian says, you have this complicated optimization problem, don't cry. It's easy. It's easy to handle it. How? Let's make it unconstrained. So I have the cost. Now I add the constraints as soft penalties. This, with some weights. With some weights. You can see these weights as regularization parameters. In classical optimization, they call it, again, naming is not important, but what do they call it? Call it in two ways. They call it either Lagrange multipliers, these lambda 1, lambda 2, and nu, or dual variables. You can call it regularization parameters. Do you get it? Yeah.
You just do this. How can you just take your arbitrary and throw them out the window and say?
How do I what?
Why are you allowed to just take your hard constraints and just throw them out of the window and turn them into soft?
This is one of the interpretations of Lagrangian. There are a lot of other theory behind it, but I'm just interpreting it. But why are we? So again, this is not just for Lagrangian. You can see the soft penalty. Why? Because it makes it simpler to handle. However, it is an approximation to the answer. So the solution to this optimization problem is approximates that. Of course, it's not equal to that. I will tell you one technique that we make it regularized, but it is exactly equal. I will tell you in the next slide. But this one at least is an approximation. Simply because here in this case, g of x must be less than or equal to 0. Here it might be 0.001. And why is it a good approximation? Because you have to make g of x small. Otherwise, it will blow up the constant, the regularized objective function. Assume g of x is 10. What happens? Of course, the cost is very bad. The cost must be small. Therefore, it's a good approximation, but it's not the exact solution. Did I answer your question?
Yeah.
Kind of, yeah. Maybe if I find a better answer, I'll come and tell you later. If you find a better solution, let me know. Thank you. So again, this was Lagrangian, and then the thing is that so now it becomes, assume Lagrangian says the Lagrange multiplier methods. It says rather than minimizing this optimization problem, which is complicated, minimize Lagrangian. And this minimize Lagrangian, there is no constraint. What do? Back to high school, first order optimality condition, right? Take derivative, set it to 0. However, in Lagrangian, now this time, this was minimized f of x with respect to x subject to these constraints. However, here I have minimized Lagrangian with respect to what? Of course, one of them is x, which was already the optimization variable. However, now we have lambda 1, lambda 2, new. What should the dual variables be? What should the regularization parameters be? Right? Therefore, simply we can say in the method of Lagrangian, say take derivative of Lagrangian with respect to each of the optimization variables. With respect to x, set it to 0. With respect to lambda 1, set it to 0. With respect to lambda 2, set it to 0, etc. And you solve it. This is called method of Lagrange multipliers in optimization, in classical optimization. This was just in parentheses, out of the scope of this course, okay? But the previous slide, this slide is in the course, the soft penalty. The next slide, which I said, interpretation of Lagrangian, that was just in parentheses for interested students. Okay, so what were I saying? Here, in this case, we usually choose lambda ourselves. And we usually let it be some small value, such as 0.1. Okay. Now, how can we make it regularized cost and let it be exactly equal the solution? Let it be exactly equal to the constraint optimization problem. How can I do that? Yeah.
Can you make it really big?
Really, when it is not satisfied, you mean, right? What do you mean by really?
I think make the lambda really big, so it puts a lot of weight.
Okay, so one suggestion was let's make lambda very big, so it is forced to satisfy the constraint, right? Something like that, if it can. However, if we do that, then we will forget the actual cost function f of x. If lambda is too big, then it disappears compared to lambda g of x, right? So maybe not. Another solution. So yeah. When I mean limit f of x plus lambda g of x, lambda to infinite. The f of x disappears. Yeah, of course, it doesn't disappear completely, but I'm saying that its value is ignored, at least up to some level. I don't want to ignore my f of x. You understand what I'm saying?
Yeah, I guess it's like I get it.
Yeah, you shouldn't make lambda too big, otherwise, okay, it doesn't disappear. It almost disappears. It almost is ignored. Will be ignored if I do that. So I think you went to the good path. So you said let's make lambda big, right? What have we added? Lambda g of x. You said let's make lambda big, and I said it's not a good idea, maybe because f of x is ignored. We have another thing, which is g of x. Let's make g of x too big if it is not satisfied, right? What do I mean? The constraint was g of x is less than or equal to 0. Let's say, rather than lambda g of x, I say lambda something, and that thing becomes very big when g of x is not less than or equal to 0, when the constraint is not satisfied. Do you understand? Now let's exaggerate. Let's make this thing star infinite when g of x is not satisfied, less than or equal to 0. Infinity for minimization. Infinity kills the optimization. For maximization, minus infinity kills the optimization. That's why I use the word kill. Right? So, in simple words, I have some constraint. Let me kill the optimization problem when it is not satisfied. So I say, I define indicator function for x being in the set S. Here, in this case, x being in the set S means g of x is less than or equal to 0. Right? It can be anything. It can be. This S might be very complicated based on the constraints. Indicator function, I know, maybe in your mind, because in many of our courses, also in machine learning, whenever we say indicator function, it is 0 when it is satisfied. It is 1 if it is satisfied, otherwise it is 0. So you see it is binary, right? However, in optimization, it's the other way around. When it is satisfied, it is 0. When it is not satisfied, it becomes infinite. Why? Because 0 is a neutral for addition, right? It doesn't do anything. However, infinite kills the addition, kills the optimization cost function. Did you get it? Yes. Yeah, you can drop lambda. You can drop lambda. Why have I put lambda? Because in the next slide, I'm gonna again approximate this indicator function. That's the reason I have kept it. So did you get it? So what does this do? It says if g of x is less than or equal to 0, then this term becomes 0. Good, and we minimize f of x. If it's not less than or equal to 0, this term becomes infinite and kills the optimization. So the solution of this is exactly equal to the solution of the constraint optimization problem. Yeah. Yeah. Yes, exactly. I said it. So in minimization, infinite kills the optimization problem. In maximization, minus infinite kills the optimization problem. Yes.
Wait, so why would we use this compared to just the constraint R10?
Why do we use this compared to constraint optimization? Yeah. So there are algorithms, optimization algorithms for solving constraint optimization problem. One of them is interior point method. Okay. Those are in classical optimization, right? However, I'm saying that in this course, we don't want to solve the optimization problems using classical optimization. We want to solve them by search. In search, how do we deal with the constraints? It's hard. Let's embed them in the cost to make it unconstrained. This is just for simplifying the problem so we can solve it using search. Yeah.
You say infinity kills the optimization problem. Like my naive brain going back to high school is thinking optimization as in take the derivative and set it equal to 0 to find like the minimum. And so like I'm thinking, okay, the derivative of like infinity. Could you just explain how infinity will like kill the optimization problem? Doesn't it depend on the optimization algorithm you're using?
So simply, when it becomes infinite, whether you are solving it iteratively or whether you are solving this optimization problem, equation 10, you can either solve it iteratively or in one shot. Okay. In both cases, either it is in one shot or it is in one of the iterations of your iterative algorithm. Okay. When this term becomes infinite, what happens? You are minimizing infinity. Can you minimize infinity? So I'm saying that minimize infinity with respect to x. However you want to change x. The cost is infinity. That's what I mean. Do you understand? Yes.
After finding function, if x is a piece of set, then lambda times 0 is 0. And if one times the piece of set, x lambda.
Yes, so again, why have I used lambda here? We can drop lambda, but I have used lambda here because in the next slide, I'm gonna approximate the indicator function again. Any other question? No? Okay, so now we have indicator function. Everything is nice in mathematics, but in computer, no. We can't implement infinity in computer, right? So let's approximate the indicator function again. So what is the indicator function? It's this. Do you see that? This is indicator function. It's 0 for g of x less than 0, or y here it is yi of x less than 0, less than or equal to 0. For greater than 0, it becomes suddenly infinite. Right? So it's like this. It's very sharp. It's not as smooth. Let's make it a smooth. Let's make it implementable in computer. So we can approximate it by these functions, right? This function is formulated as this. Minus 1 over t logarithm of minus yi of x. Right? And t is a parameter, hyperparameter. T is greater than 0, usually a large number, such as 10 to the power of 6, as much as the computer allows. Okay? Then, of course, the approximation becomes more accurate when t goes to infinity. So what do I mean? Here, t is increasing. So as you see, by increasing t, I have a better approximation. Then, as you see, now this becomes a smooth. This becomes a smooth, and I can replace the indicator function by this logarithm function. Right? Therefore, when you use this, especially combined with Newton's method is out of the scope of this course, just for your information, I'm saying that. When you combine this plus Newton's method, they call it log barrier method. Also called interior point method. There are different names for the same thing. Why do they call it barrier method? Of course, it's a barrier. It doesn't allow this to go to an invisible set. It's a barrier. Why do they call it log barrier? Because they are using logarithm function for approximation. Yes.
But eventually, this will still go to infinity.
So multiplying, no, add it to the cost, right? In which.
But this essentially will eventually go to infinity. But is the advantage of this just that since it happens more gradually as t approaches infinity, it's less computationally heavy? Yes,
exactly. It goes to infinity gradually, as you see. Doesn't become infinite suddenly. That's the reason. Also, it's a smooth. So you can see that both it gradually goes to infinity, so it's good for computer. Also, it's just good for derivative. It's a smooth. Yeah.
I understand that with this approximation, it's not necessarily infinity, but if the point of this is still just to kill your optimization problem, I'm still not understanding why we need lambda here.
Here we need lambda because it doesn't go suddenly to infinity. So assume it's a big number, but I control how big I want the impact to be by lambda. The big number times lambda, right? I'm just putting lambda to give you more control. You can drop it. If you drop it, it means that you have set lambda to 1. Right? Yes. Okay. So yeah, as I said, it's also called the interior point method in classical optimization. So let's compare these things. Let's compare these things very fast. Someone asked a question in Piazza, I also answered that. So what here we have a constraint hard penalty, equation 7. Here in equation 8, we have unconstrained soft penalty. In equation 10, we have unconstrained hard penalty. In equation 11, we have approximation of unconstrained hard penalty. So just give me a second. Equation where were we? Equation 7, which is constraint hard penalty, and equation 10, which is unconstrained hard penalty, have exactly the same solution, right? The solution of equation 8, which is unconstrained soft penalty, is an approximation to equation 7 or 10. Also, the approximation of unconstrained hard penalty is also an approximation to the solution of hard penalties. Did you understand? So someone had question first. Yeah. What can you be louder a bit? I didn't completely understand your question.
So this is used for the value, right?
Yes, yes. Yes.
So the context of the computer, why would you just check value less than 4?
Okay, so the question is, why do we check whether, rather than these things, that why don't we check every time whether y(x) is less than or equal to 0 or not? If you check it, it's kind of indicator function, kind of. Also, in classical optimization, which is not in this course, sometimes we check, and if it is not because it is iterative, in each iteration we check. If it is not in the feasible set, we project it back to the feasibility set. Okay. In also that, for example, projected gradient method uses that technique. So answering your question, I'm saying that if you check every time, you're kind of doing the indicator function manually, but also there are some techniques in classical optimization. We check, and if it's not satisfied, they project it back to the feasibility set at every iteration, such as projected gradient method. Okay, you had a question?
Yeah, with the logarithmic approximation, like as you get very far into the condition you want to get, could you have like a very great impact on the minimum? Like if I wanted to keep x less than 0, as I get further and further down, it would more and more greatly affect what my minimum on the whole thing would be. So could you run into situations that would be a
So you can I didn't completely understand what
like say I wanted to minimize f of x is x squared, and then I have this indicator function added to it. But as I get very far into the negatives of x, it would be x is 1,000, x is 100,000. Your logarithm still it continues to increase, and you still get a negative benefit on your minimization problem.
Okay, so you mean when x becomes too much negative, you are getting unsatisfied in the you are not so you are getting worse and worse, you mean, in every iteration?
Yeah, would that benefit your minimum? Certainly. because it'll blow up as you get towards zero asymptotically, but it'll also continue to decrease forever.
I believe whether you use search methods such as materialistic optimization or classical optimization, you never go in a direction which either makes your cost worse or your feasibility set worse. So you will move toward a direction which at the same time minimizes your cost and satisfies your feasibility. You don't go in that direction. You don't get worse and worse. You get better and better. You converge, you don't diverge. Okay, any other questions? Yeah. So simply, first up, this is barrier. Do you agree? This is a barrier, and we are approximating this barrier using a logarithm function. Hence, we name it log barrier. That's the reason. This is an approximation for the indicator function for yi of x to be less than or equal to 0. Yes. Do we still need lambda? But I think you may drop lambda, but T here controls how accurate my approximation is. Lambda controls how much I should care about feasibility compared to actual cost. Yeah, kind of. Again, but as I understand what you're saying, multiplication of two hyperparameters, you can see it as a new hyperparameter. I understand what you're saying. Okay, so let's move on to the class was until 9:20, right? 9. Let me cover another topic and then we'll have a break. So give me. No, it's not break yet. Okay, so the first materialistic optimization algorithm, and that's local search. Okay, this is the simplest materialistic optimization algorithm, also called hill climbing. I'll tell you why it's called hill climbing also. So in local search, also called hill climbing algorithm, what do? We get some neighborhood. So assume I am in the land, somewhere in the landscape, optimization landscape, right? We get some neighborhood and we search for the best fitness value among different points in the neighborhood. So what do I mean? Assume I'm in the landscape, and then around myself, in a neighborhood around me, I search. So what? I think it's obvious, right? So here I have some cost. The optimization landscape that I'm standing, I have some cost. I am an x. I fit myself to the function f of x, gives me some cost value, f of x, right? Then I see my neighbor, somewhere my neighbor. I grab, this is x, feed it to f of x, it gives me some function value. Do this again. So I search. Let me see where the function value is minimized. If I find a better solution, I update my best solution so far. So initially, my best solution is where I am. Then I search. If I find a better solution, I update my solution. So the algorithm is like this. Local search, initialize the solution x while not converged. First, generate neighborhood n of x. So n of x here stands for neighborhood of x, right? So I mean, it can be any set around x. You define it. Whatever you define it, you make a new variant of local search, right? So someone says, I want it to be a sphere around me. Whatever, hypersphere around me. Someone said, I want it to be a hypercube around me, right? I think hypercube for coding in computer is easier. than hypersphere. For hypersphere, you need to take the radius, right? Doesn't matter. So you define the n of x and you search. For points in the neighborhood x, in this line, you can either search for all of the points in neighborhood of x, or for some samples from neighborhood of x. Here I mean, by this notation, I mean sampled. By the way, don't confuse with the normal distribution. Here I mean neighborhood of x. Okay, for either for all of the points in this neighborhood or for some samples in the neighborhood, I evaluate the fitness function or the objective function, right? If better fitness, what do I mean by better fitness? Better objective value, it means if I am minimizing, it means that I find a less function value. If I'm maximizing, I find a larger function value, right? If better solution, then I update my solution, right? And this step is optional, whether breaking the inner loop or not. I mean, by inner loop, I mean this. First off, I think all of you guys, I assume you know coding. Otherwise, okay, if you don't know what is breaking a loop, it means I come out of the loop. Okay? By the way, I have uploaded a video about Python. Feel free to watch that if you are not familiar with Python much. Okay? You can watch that and ask me if you have any trouble or problem with coding. Because in this course, at least in the tutorials and in the assignments you will implement some of the algorithms yourself, and I think it will be very cool. Assume you do search yourself on some objective function. Okay, so what are we doing here? What is this optional thing? If I break the inner loop, what happens? It means that in my neighborhood, if I find a better solution, I jump there. Then I find another neighborhood around me. I search again. If I find a better solution, I jump there. Again, I define a neighborhood around me. If I don't break the loop, what happens? It means that here I'm searching several times, several things. And if I find a better solution, I don't jump. I still keep searching in the neighborhood. Maybe there is a better solution. When I'm done with my search in the neighborhood, then I jump to my best solution so far. Did you understand the difference? That when I break, it means that whenever you find a better solution in your neighborhood, jump there and define your neighborhood around that again. But when if I don't break the loop, it means that I don't jump. I keep searching until what I want. Then I jump to my best solution so far. That's why I think it's called local search. I'm searching locally. Why do they call it hill climbing? Because as I said, you can see the optimization objective function as a landscape, and you are like on a hill and you are climbing it down or up. If you are minimizing, you're climbing it down. If you're maximizing, you're climbing it up. It's like hills, right? In the landscape. You understand? I agree, it's very simple and maybe boring, but it is the simplest materialistic optimization algorithm. And actually its effect, it's intelligent. It's not random search. It's intelligent. You're moving toward better solutions. So an example is here. I'm here, I find a better solution, then I come here, then I find better solution, I come here until I reach this local minimum, right? What is the problem with this algorithm? Can you tell me? Exactly, it will get stuck in the local minimum or local best, because if you are maximizing, it will get stuck in the local maximum, right? So the problem is that it's getting stuck in the local best. Here, I started from here and I found the global best. But what if I start from here? I will go down and I will find this local best, which is not the global best. while I never saw this region. Right? I can say this problem of local search exists for all of the materialistic optimization algorithms. Whenever you are searching, even intelligently, you are prone to get stuck to the local best. So you should decide whether you want to do classical optimization, do the math, do the hard work, or if you're lazy, you should accept that. You might get stuck in the local best using intelligent search. Okay. However, some algorithms, some materialistic optimization algorithms are dumber than the other ones. So they are more prone to get stuck to the local best, right? So we have different algorithms, and whenever someone publishes a new algorithm in materialistic optimization, what do? They say, they always compare with the previous ones, and they say we found a better solution. The previous ones got stuck in the local best. So it's a good technique for you guys if you want to publish in these areas to design algorithms which get stuck in the local best less, right? Okay. Now let's improve the local search, not to get stuck, at least as much as it can. Of course, it never can get perfect, but let's improve it. So as I said, local search is prone to get stuck in local best. We can improve local search in various ways. One of them is iterative with different initializations. So for this, we have two algorithms: multi-start local search and iterative local search. We can change the objective function or landscape for simplifying the problem. Okay. So for this, we have three things at least: guided local search or GLS, smoothing method, and noisy method or jitter. By the way, when I introduce these techniques, some of these are not just for local search. You can use these algorithms even in your own algorithms, your designed algorithms, in your own research, in your other areas. So these are just ways of thinking, right? Don't restrict yourself to these algorithms. Try to learn this and go above them, go beyond them. Okay, so we can use different neighborhoods, such as variable neighborhood search or VNS. Sorry. You can have variable neighborhood search or VNS and generalized neighborhood search or GNS. Or we can accept non-improving neighbors, such as simulated annealing. We will explain it later, right? So let's go to each of these one by one. First, iterative with different initializations. I think the first thing which comes to your mind is this: how can we improve local search? Let's have different initializations, right? But we can do it in two ways. The first way is multi-start local search. What does it do? After finding the local best by local search, we sample a point in some neighborhood of the solution that we found, and then we restart the local search algorithm from that point. As the algorithm is, we can do this for several times, by the way, and select the best solutions among them. So simply it means that whenever I do some local search, I find, and the local search says that this is my best solution. I say, okay, let's around this best solution, let me start another local search from a point around this local best. So the local search gave me some solution. I start another local search algorithm with the initialization of a neighborhood of that solution. Obvious? Is it clear? So simply it says that for multiple times, the more times, the more accurate might yes. Yeah, so exactly. So
Begin with.
exactly. It's a good point that you mentioned. So the question was, but what if we start from the neighborhood around that and we get stuck in that the same local best again and again? So the solution is that what? The solution to this question is that let's increase the neighborhood for when we are searching, right? So what do I mean? The local search gave me some solution. Do you remember I said in a neighborhood around that, initialize the next local search. Let the radius of this neighborhood be big. Then you might go to some other parts of the landscape and search and find some better local best. Do you agree? Of course, you never find out whether that local best is a global best or not, but you hope, right? You hope. In materialistic optimization, we always hope, right? So, did you understand the question and what the explanation? By the way, one important thing which I forgot to say in the local search, the neighborhood X in the local search, it can be fixed or you can make it dynamic. What do I mean? We are in a loop, while loop, right? We're doing it iteratively. Maybe you say, initially, I want to explore more. Later, I want to exploit. So you can say in initial iterations, let my neighborhood be big, large. In the later iterations, let my neighborhood decrease. Right? Do you understand? The bigger the neighborhood, the more exploration. Do you agree? The bigger, the more exploration. And the less exploitation. The other way around. The less the neighborhood, the less the exploration, the larger the exploitation. Do you understand? Therefore, the neighborhood X can be dynamic. So in initial iterations, you might say, or it might be fixed. So these are different variants of local search, right? Do you understand what I'm saying? Yeah. I defined that in the previous session, but let me explain it again. What is exploration versus exploitation? So to recall, exploration means that I explore more in the landscape. Exploitation is the other way around. Let me do the search locally more. So they are opposite of each other. The more you explore, the less you exploit. Exploration means that let me search different parts of the land optimization landscape. Exploitation, it means that let me search locally. You understand? And I gave you an example in real life. I said you can explore and exploit in your life. Usually human explores first, then exploits, right? This is exactly the behavior of human society. Humans, when they are young, they explore. Gradually, they settle down and they exploit. Materialistic optimization also is like that. They usually explore first, and then they exploit later, usually. Did that answer your question? Okay. So as I said, n of x, neighborhood of x, can be dynamic. So we were back to the multi-start local search. What were we saying? We're saying that whenever we find a solution by the local search in a neighborhood around that, let's start another local search. And if we make the neighborhood for this restart big, then hopefully we can find a better local optimum. So again, for multiple times, do the local search, then append the solutions, store the solutions, right? then sample from the neighborhood and do another local search again. Do it for multiple times, and then return the best among the solutions. Okay. Oh, by the way, sorry for that. Okay. So the next thing is iterative local search. Someone might say, why do I need to restart from a neighborhood around that? Let me completely restart from a random initialization, right? To also resolve the issue of whether I want a big neighborhood or a small neighborhood. Let the neighborhood be the whole landscape, right? So I do local search for multiple times, but each time I start with a random solution in the whole landscape. Hopefully, I find a better local optimum. An example is in this figure. I start one here from here. The first local search converges here. Then the second one starts from here. It converges here. The third one starts from here, converges here. Fourth one here. The best among them is the solution of 2 and 3. Right? So, of course, the more number of times you do the local search, the more accurate, the better local best we can find.
Does the algorithm know that the best between 2 and 3 is the same one?
Actually, the best of the 2 and 3 might not be exactly the same because you are jumping, you're searching, you might not find the exactly same solution here. They might be a bit close to each other, but one of them is better. But in ideal world, they are the same. They find the same solution. Yes.
So in the iterative local search.
Yes, I think iterative local search is better than multi-start local search, and you can see it as a special case of multi-start local search where the neighborhood is the whole landscape. Yes.
What would be the trade-off of using ILS instead of multi-star? Would it just be more computation needed to source the elements?
What is the, why don't we use ILS? What do you mean? Why do, yeah. So if you want my answer, I say always use ILS rather than multi-start. We want to cover different variants, but ILS is better, right? Yeah. Yes. Any other question? No. By the way, for each of these, you can simply calculate the time complexity and these things, right? It's not that much hard. For example, time complexity of these, if it is O whatever, assume the local search is the number of iterations that you OT assume. T is the number of iterations per local search. Assume you do it for A times, then the whole thing is OAT, right? Big O notation, I mean, doesn't matter. I think that's simple. If you don't know what big O on the notation is, don't worry. That's just for interested students. Okay. The next category is change in objective function. Guided local search, it was proposed in 1997. Reference 3. It modifies the landscape gradually. So it modifies the optimization landscape. So another way to improve local search is let's change the optimization landscape gradually. Okay. So it modifies the landscape gradually to simplify the landscape so local search does not get stuck in the local best. Okay. GLS does not work on all problems, at least as much as I understood. Okay. When I studied the algorithm. For using it, the features should be represented as binary. What do I mean by existing or not existing? So whether the feature exists or not, 0, 1, right? When you have the features binary 0, 1, it means that specific feature exists or not, right? 0, 1. Do you understand what I'm saying? These algorithms are meta-heuristic optimization algorithms. Recall preliminaries. By the way, if I didn't tell you or not, in my courses, I refer to preliminaries a lot. So preliminaries are very important. So meta-heuristic versus heuristic. What was that? Meta-heuristic optimization is for all, doesn't care about your optimization problem. So features can be anything, right? In this case, I'm saying that the features must be binary. An example now, assume, I don't know, my cost is, what do we say? The design of the city. The problem is the design of the city. The cost is the pollution of the city. How do we design the city that the pollution is minimized? Something like that, maybe. Then the features can be, for example, whether in this region there is a house or not. Maybe another feature might be you define your problem. You understand what I'm saying? The features are binary here. Then if it is, I'll try my best that in your assignments you see some examples for using meta-heuristic optimization on problems. I will try to do that. So if it is not binary, assume your features are not binary, then what can we do? We may be able to convert it to binary string when you have, so in two ways at least. One way is that assume your feature is a floating point vector. Then using a threshold, make every feature binary. If every feature value is less than half, for example, is 0, greater than half is 1, right? So you can use threshold. Another way, assume you have a float, a scalar float. Assume your x is a scalar float. Now you can make it a binary vector because you can represent every float value, decimal values as a binary string. Am I right? Okay. So in these two ways you can do that. Then x1 to xt are, what does this mean? A d-dimensional vector whose elements are 0 and 1. Right? I think I should say this, sorry. Then assume in some iteration of the local search, the solution is this. Okay. Then now I'm define ij of x as 1 or 0. If xj is 1, because it's binary, right? It's either 1 or 0. If xj is 1, it means that xj contributes to the solution because this is the solution. Then xj is 1, then I let ij of x to be 1, otherwise 0. So you can see ij of x as indicator function whether xj is 1 or not. In GLS, every feature xj should also have some cost cj. That's why initially I said this GLS algorithm is not applied on all optimization problems, on specific problems where your features are binary and every feature has some cost cj. Okay, for example, and then you might have an overall cost which can be the summation of the costs of the features, right? We also define the utility function for the solution x. These are just definitions, right? I'm gonna use them. Uj of x, utility function of x, is ij of x, which I defined in equation 1, times cj, which is the cost of the jth feature, over 1 plus pj. Pj is the penalty for the jth feature, initialized to 0. Again, we never should be scared of these formulas because we never memorize them, right? We just understand them and use them. In this course, do not memorize anything. Yes.
Why do we define indicator function for a variable that's going to be binary anyways?
Yes, so maybe you can replace ij of x with xj. Yes, I agree.
As
Yeah, yes. You're right. So why am I using ij of x? Because in their paper they use that. Okay. So pj, j goes from 1 to d, right? We have d dimensions. And these are the penalties initialized to 0. So initially, all of the penalty of the features is 0 for all of them. Every time we see which of the utilities is the largest. So every time, it is iterative. In every iteration, we see which utility is larger. What does it mean? So what is in utility? When utility is larger, it means that first off, it is 1, xj is 1, so it is contributing to the solution. If the feature does not contribute to the solution, the utility becomes 0. Right? So first off, it must contribute to the solution. It means that it's important for my solution. Yes. Feature means dimensions. So I have a vector. Every element, I call it feature, element, dimension. These are used interchangeably. Feature, dimension, element of the vector. Okay. And in real world, I gave you some examples in the previous session. For example, if I have health data, features can be, for example, I have a feature, I have a vector, and each feature, for example, is blood, fat, blood, sugar, blood pressure, etc. Right? We have different features. We can represent them as one vector. Yes. Yeah. Yeah. So, as I said, the vectors, the data x is just a strings of 0 and 1. So they are binary vector. I have to have that. GLS doesn't work for all optimization problems, for just for specific optimization problems where your features are binary. Yeah. I will. The break will start soon. Just give me some time to finish this part, and I can't make the break in the middle of this. So, as I said, you have utility, and of course, when I say utility, it means good, right? Benefit, something like that. So I want it to be large, and utility has the indicator function. So it means that I want the feature to contribute to the solution. Also, its cost is big. What do I mean? So choose the feature which is worse for the optimization. The cost is big. That feature which is contributing to the solution, its cost is big. It's an alert, right? I want to find the alert. And I have some penalty in at the end, in the bottom, in the denominator. Why? Because I don't want to choose the same feature over and over again. Every time that I choose a feature, I penalize it. Therefore, the denominator goes up. Therefore, I don't choose it next time. When the denominator goes up, the whole thing comes down. Did you lose me? Okay, I think you're tired. So let's come back at 8:30. Let's have a break, and then we'll continue. Okay, so let's continue where we were. Let me go a bit faster because we need to cover things. But I will make sure that you explain clearly. So what were we saying? GLS simply, its idea is the same. It's simple. It says I have some cost function. Okay, let me modify it so I don't get stuck in the local minimums. How does it modify it? I will tell you. So assume this is the local minimum. It makes this part, which was convex, concave. So I get out of the local minimum to be able to find other local values. So this is what GLS does. And how does it do it? I'm explaining it to you. The thing is that it's not applicable, at least as far as I understood, to all optimization problems. Your features need to be either binary or behave like binary. When I say exist or not exist, you can see a floating point with some condition to be existing or not. Doesn't matter. It needs to behave like binary, whether it exists or not. And then, so what we're I saying here, the idea of GLS is this: let's penalize the features which exist in the minimum solution of optimization. So what do I mean? I have some local best found by local search, and some of the features contribute to that, right? Let's penalize them because they are contributing to the local best, and I want them to be to the cost to be opposite in that area. So I penalize them. Did you understand what I'm saying? Okay, and this penalization, I do it by regularization that I talked about in the preliminaries. So I have the actual cost, I have some lambda as a regularization parameter plus lambda, this. And what is this? Penalization of each of the features, J goes from 1 to D, which exist or which contribute to the local best, right? In this point, which is my local best, some of the xj's are 1, some of them are 0, right? Only for the ones which are 1, I penalize them. And how do I define the penalty? In this way. I calculate the utility function, equation 2, for each of them. Just give me a sec. I calculate them for each of them. You wanted to ask a question? No, okay, that's fine. You calculate the utility for each of them, then find the largest utility. What does a largest utility mean? It means that first off, it contributes to the solution. Secondly, its penalty, the previous penalty is low, because if the penalty, its previous penalty was high, the denominator gets large, the whole thing becomes low. Thirdly, its cost is bad. Its cost is large. Then what happens? So I define this. Why do I have this penalty in the denominator? Can you tell me? We use this idea a lot in science, in different algorithms. Since I've seen that a lot. So as I said, you need to understand the ideas. You can use them anywhere. So here it says, let's not penalize the same feature or the same person all the time. Let me penalize you first, but the next time I'm less keen to penalize you because I already penalized you once. Let's give others a chance to be penalized. Do you understand? This is exactly what it is doing. And why do I have this +1 in the denominator? Try to understand everything. Why do I have 1+? Because I don't want to have division by 0. Initially, all of the PJs are 0. Right? Okay. So I have this cost, regularized cost, and this is what GLS does, kind of. Right? The regularized cost function finds the local minimums and penalizes them to become peaks rather than valleys. Then the cost function becomes smoother and easier to find the global minimum, right? This is the algorithm, GLS. So we have to initialize the solution X as a binary vector. If it is not binary, we have to make it binary, or at least behave like a binary. Then we have iterations, do the local search with the cost. Why am I feeding cost to the local search algorithm? Because every time the cost is changed, the cost is the regularized cost every time. Here we are updating the cost to become the regularized cost. And then I have this, I append the solution, then I have a for loop. Then for each of the features, I calculate the utility. Then I find the maximum utility. What does argmax do? It means that, I think we talked about it in preliminaries. Among these, which one is the maximum? Which index is the maximum? And then For that one, which has the largest utility, I increment its penalty. And then I regularize the cost and feed it to the landscape to search in that regularized cost. Finally, I return the best among the solutions. Okay. I agree. It's a bit weird. This algorithm is a bit weird. I agree. Okay. But I think the other algorithms which we'll go through are more straightforward. But we had to cover it because it was an important algorithm in local search. Why? So the idea of this category, do you remember I said we can do several things to improve local search for not to be prone to getting stuck to the local search, to local op best. One way is changing the objective function. And GLS is one of the ways to do that. Let's modify the objective function every time. Right? That was one. Okay. So the other way to do that, let's smooth the objective function. What do I mean? Exactly, I think this, and by looking at this, you'll understand very well. So initially, let the objective function be like this above, the figure above. So this is a global best, but we have a lot of local bests, right? Let's smooth it a bit, smooth this objective function. What do I mean? Let the valleys be less valley. Let the peaks be less peaky, peak or whatever we call it. Okay, so the valley goes up a bit, the peaks go down a bit. So it becomes a smoother. Again, we can smooth it further and further. When we do that, you'll see that the local bests or local minimums are disappearing gradually. And we'll end up with only global bests. Do you understand? Interesting. And how can we do the smoothing? Again, these ideas, you can use them anywhere. One technique is window averaging, right? So assume in your domain. So you can use this window averaging. Usually it's used for time series. Here, I'm not using it for time series. Here, I'm using it for another reason. So I assume I have the domain of my function. Do you agree I can have grid? I can have a grid, right? So every point in this domain has some neighboring points in this grid, right? In 2D, it's a grid. In 3D, it's the cubes. In high dimensions, there are hypercubes, the grids, I mean, the corners of the hypercubes. So we have the grid. So every point in this domain of the function has some neighbor points. You don't agree with me? Consider this. Simple, if X is one-dimensional, this is my cost. I can have the grid like this. This point has some neighbors. This, right? The neighboring points have some cost value, right? This point, its cost value is f of x. Do you agree? Also, I have a bunch of f of y's where y's are in the neighborhood of x. A bunch of them, right? Do you follow what I'm saying? So I have a bunch of neighbors. Therefore, I have a bunch of cost functions, cost values for them. Take the average, replace f of x with the average of fy's. So I'm simply replacing the cost value of every point by the average of the cost values of its neighboring points. Agreed? In this way, it becomes a smoother. The function becomes a smoother. If a point is too low, too valley, and its neighbors are high, it means that it's a sharp valley like this. It is replaced by the average. So valley comes up. The other way around, if it is too high, too mountain, too peak, it comes down because of its neighbors, right? So it's a smoothing technique. Therefore, gradually I can smooth the function and do the local search. So smooth the objective. I can have the landscape f, window size s. Again, window size s is a hyperparameter When I say hyperparameter, it means that the user can define, right? Parameters are usually learned, especially in machine learning. Parameters are learned by optimization. Hyperparameters are chosen by user. Okay. So we make a grid with some fine step. The steps need to be fine, right? Otherwise, the smoothing will be, I think, not good. It will not be accurate. In the domain of the landscape, then initialize the smooth landscape G with F. Initially, the smooth function is the function itself, right? Then I want to iteratively, then I want to go point by point in the domain. For each point in the grid, in the domain, I smooth it. How? I have the sum initialized to 0, neighbor counts 0. Then for each neighbor y in the grid in window of size S around X, so I have X, I have some points in the grid around it with some neighborhood S, right? With some window size S. Then I sum the cost values of all of them. Here, by dividing sum over the neighbors counts, so how many neighbors do I have? This becomes the average of the FYs. I have several FYs, right? The average of them, I replace the cost of that point by the average. So then G of X becomes a smooth. Now I'm gonna use this algorithm in the local search. So I initialize the solution X with the window size S. I do the local search on the landscape. Then every time I smooth the objective function with the window size S. And then I feed this landscape again to the local search, right? Gradually, I hope that the local minimums disappear, so X can find the best, so X can get out of the local best and find the global best. Finally, we return the best among the solutions. Do you agree? The window size S, again, can be fixed, just give it fixed or dynamic. So maybe, again, these are, I think it's better to be dynamic. Why? Can you tell me one thing? Here, for t equals 1, I have less smoothing. Gradually, I want to smooth more and more. So I can either smooth the smooth function, it becomes a smoother with a fixed window size. So what do I mean? I apply a smoothing on this, it becomes t equals 1, this one. I apply a smoothing on t equals 1, it gives me t equals 2, right? At the same time, I can modify the window size S. But for the simplicity, I think the easiest for you to understand, assume S is fixed. Even if S is fixed, this behavior holds. Why? Because in t equals 1, I have a smoother version of t equals 0. Then when I smooth the t equals 1, it becomes a smoother again. The smoothing. It becomes a smoother and a smoother and a smoother. Yes. So the question is that, assume I have something like this. This is my global best, global minimum. Then the algorithm misses that. No, why? Because it gets smoother and smoother. It's coming up and up. Still, the argument is the same. The argument is important to me here, not the mean. Recall preliminaries. Argument is here, right? When you bring it up and up, still it's below the other values. So the argument stays the same. Yes. What?
Doesn't it depend on the step size? Like if it's too sharp and your step size is too large, then it's possible for you to jump over it because getting discrete values.
I agree that the step size needs to be fine. It needs to be small to be accurate. Yes. What?
so you have some local minimum that's like relatively low to didn't have like a very sharp actual global. But that global one become higher than this.
No, I disagree. So the question is this: assume like this. Is it a case that when we smooth, this goes upper than this one? No. You're saying that depending on the curvature here, maybe this case something happens that this smoothing comes upper than, so it becomes like this. Then we'll have error. I'm saying that as we are doing it iteratively, and in each iteration we are finding the best solution. Maybe in the previous iterations, hopefully we have found this. If not, I agree that it's never perfect. It's never perfect. Do you agree? Yeah, in each iteration we search and we append the solutions. Finally, we've returned the best. And always materialistic optimization algorithms say this is the best that I could find. Yeah. So you had a question? Okay, so great. So yeah, that the smoothing, we talked about it. And we already talked about this. Now noisy method or jitter. That's also used a lot in classical optimization. So not just for materialistic optimization. So every time you find a solution, add some noise to it and search again, right? The noise that you add is also called jitter because you're jittering it, right? So in every iteration of the local search, we can add some noise, also called jitter, for the initialization of the next local search. So like this. So we have multiple times, do the local search, append the solutions, then get some epsilon from a Gaussian distribution with mean 0 and variance sigma squared. Why have I said sigma squared I? Because my x is d-dimensional, right? Therefore, the noise also needs to be d-dimensional vector. So its covariance matrix, the covariance becomes a matrix, covariance matrix. And this I is identity. When I say sigma squared I, it means that in every direction in the space, I don't care. The Gaussian is the same. The Gaussian is not like this. Gaussian is like this, right? In every direction, it's the same. It's the standard deviation is the same. And then I add this noise to x. This is neighborhood. And in the neighborhood of that point plus noise, I start the next local search, right? Also, interestingly, I can decrease or decrement the variance. So initially I have huge variance. Why do we do that? In optimization, we usually, if we want to add jitter, initially we have high noise because we want to explore more. As I said, usually materialistic optimization algorithms firstly explore and then they exploit, because at the end we are supposed to be close to the solution. We shouldn't jump. Initially, we need to explore the landscape to find candidate solutions, right?
Are we applying the Gaussian centered on the current best?
Yes, exactly. So why do we have zero mean for Gaussian? Because this is being added to the x. It shouldn't change the location of x. It's mean. It should be around x, right? So the mean of the noise should be 0. Therefore, the mean of x plus epsilon becomes the mean of x. The next category of things that we can do for improving local search is using different neighborhoods. One of the techniques is variable neighborhood search, or VNS. VNS was proposed in 2010, not too old. So it performs local search as a finite state machine. Do you know what is a finite state machine? If you have, I think in robotics, you see a lot. Also in control theory, you see it a lot. Sometimes in programming, you can code using finite state machines. So it's saying that I have some state machines, then I can go from one state machine to another one based on some conditions, right? Then it uses finite state machine for that. And what does it do? First off, we select several neighborhoods, n1 to nn. So now I have several neighborhoods, right? N neighborhoods. Then first we perform local search in the optimization landscape, some local search, right? The local search that we do, first off, we do it in neighborhood 1. So in the neighborhood 1, n1, we search. We check, but we do some local search, and then we do no local search in n1. Then we check if a better solution is found in this area in n1. If yes, we update the best solution, of course, because we found a better solution. Then we go back to the area n1 and search it more, because we found a better solution in n1. Let's go back to n1 and search it more. If not, we go to the next neighborhood, n2, and search it. Again, we check if a better solution is found in the area n2. If yes, if we find a better solution, we update the best solution, of course. Then we go back to n1 again. And we start searching from that area again. If not, we go to the next neighborhood, n3, and search it. And we do it until nn. So in simple words, the philosophy is easy. It says, let me search in one neighborhood. If I find a better solution, I go back. So it's a series of neighborhoods, right? In n1, I search. First I search, then I go to n1. I search. If I found a better solution, great, update it, go to n1 again. Search. If I can't find a better solution, I just get disappointed of n1. I go to n2. I search again. If I find a better solution, great. Let's go back and start from n1 again. Probably we can find a better solution starting from n1, right? If not, we get disappointed of n2, we go to n3, right? Then we search. If we find a better solution, go back to n1 again. If not, go to n4, like this. As you see, these are the arrows. From n1, you go either to n2 or itself. Then from n2, you go either to n3 or n1 until the end, right? As you see, if your neighborhoods are diverse, this algorithm becomes a monster. It searches the whole space almost, right? We have another thing named generalized neighborhood search, proposed in 2015. It performs VNS, the variable neighborhood search that I explained, in parallel in several regions of landscape. So it says, let's make it a bigger monster. How? I have some regions. In each region of the landscape, I do VNS, right? I do VNS in some region, maybe in north of landscape, then in the south of landscape, then here, then there, then there. Then I return the best among the best solutions of each of the regions, right? Usually they choose the neighborhoods in this way. So assume X star by the initial local searches here. Then the region 1 will be with some radius around it. And on that circle around it, or hypersphere around it, I choose some neighborhoods. Then I increase the radius. Then I search around that. Why am I always around X star? Because X star is the best that I found by the local search. I don't need to waste my time in other regions of the landscape which may not be good at all. So let me go in hyperspheres around my best that I could find. And so region 1, you can do it in a layer wise, as you see, like the layers of onion, right? So it becomes a monster. Okay. acknowledgement, some slides of this slide deck are inspired by the teachings of Professor Saeed Sharifian at the Amir Kabir University of Technology Department of Electrical Engineering. So these are the slides, sorry, the references. Now let me go to the simulated annealing. So simulated annealing. First off, guys, listen. We cover different algorithms. So we are covering different algorithms, and I think at the end of the course you will see that you have learned a lot, and I think that you will enjoy it. So Boltzmann or Gibbs distribution and statistical physics. Who here loves physics? Yeah, okay, great. So here we are talking about the statistical physics here a bit. So centuries ago, Boltzmann distribution was proposed in 1868, also called the Gibbs distribution, proposed in 1902. The this energy-based distribution, this Boltzmann distribution is an energy-based distribution, right? Was found to be useful for modeling physical systems statistically. Okay. One of these systems was the Ising model. What does it do? It models interacting particles with binary spins. So every particle in particle physics has a spin. Particle physics is also related to quantum mechanics. So it's either rotating in this way or the other way. I think you have seen these figures like this, right? They say like this, facing. So it's either rotating clockwise or counterclockwise. Then based on that, we can define whether its spin is up or down. So Ising model says that let's consider several particles next to each other, which are neighbors of each other, and see what states they can converge to, something like that. What is the probability of spins of different neighborhoods? I believe the proposer of the Ising model won the Nobel Prize several years ago. It's very important. Okay. Assume we have several particles, x1 to xt, right? Each of them can be a particle. By the way, for example, electron is a particle, right? xi to xt, x1 to xt in a statistical physics. These particles can be seen as random variables which can randomly have a state. For example, if the particles are electrons, they can have states +1 or -1 for counterclockwise and clockwise spins respectively. Spins, how do they rotate? The Boltzmann distribution, also called the Gibbs distribution, can show the probability that a physical system can have a specific state, right? That is, every of the particles has a specific state, whether rotating clockwise or counterclockwise. The probability mass function, what do I mean by probability mass function? The probability distribution for discrete variable is this. This is the definition of Boltzmann distribution. Probability of x it's a random variable, right? Here it's either up or down. Is e to the power, the Neper number, e to the power of minus beta capital EX over z. Very simple. Don't see this as a complicated thing. Science is really easy. You shouldn't be afraid of it. So what is this? Let me explain every part of it. Capital EX is the energy of variable x, energy. Z here is a normalization constant. Why? Let me tell you about Z a bit. When I have a bunch of numbers, I want them to behave like a probability. Forget Boltzmann distribution. I have a bunch of numbers, can be any value, can be 1 million, can be 10, I want this bunch of numbers to behave like a probability, right? One technique is what? In this course, I'm teaching you techniques. One technique is what? What? Exactly. Thank you. So you divide every value by the sum of the values. In this case, every value becomes between 0 and 1, and their sum to 1. They sum to 1. Like probability, right? Another technique is what? So the technique that he mentioned is that I have x1 until x d, whatever you call it. Then I simply divide each xi by the summation of xj's. J goes from 1 to d, right? In this case, each of them becomes between 0 and 1, and they sum to 1 like a probability. These techniques are used a lot in various fields of science, including machine learning. Another technique is what? I give you a hint. So e to the power of xi, what happens? What is e to the power of xi? Can you tell me? It's exactly the Gaussian distribution. Let me Google it. So Gaussian distribution. It's this, right? F of x equals 1 to the something, e to the power of something, right? So when you have e to the power of something, it becomes like a Gaussian distribution. Or in general, it becomes exponential family of distributions, right? It's exponential. So I can say I want my probability to be like a Gaussian distribution. Why? Because Gaussian distribution is the most famous and happening distribution in the world. In nature, the most distribution that you see is Gaussian distribution. Even the cells in our eyes work like Gaussian distribution. So let me make it Gaussian distribution. So I have e to the power of xi. Now I want to make it again like, however, do they sum to 1? No. So I can say divided by summation of e to the power of xj's. Right? Simply I can say divided by some value z. I don't care, as long as they sum to 1. And here in this case, z is summation of e to the power of xj. So I always need a normalization factor. I need to divide them by the normalization factor, so they become between 0 and 1, and they sum to 1. By the way, what is this? Sorry, I apologize. So did you see what I wrote? To e to the power of xj over sum of e to the power of xj, and I can replace this sum of e to the power of xj by z, some normalization factor. Why? Because I want them to sum to 1 and be between 0 and 1, also behave like a Gaussian distribution, e to the power. What is this, by the way, in machine learning? It's softmax form. Okay, it's exactly the technique used in softmax form in optimization. This is called softmax function. If you don't know what it is, that's fine. Just know that this is softmax function. Softmax function is exactly this hack. Let's make it like behave like a Gaussian distribution, yeah, and sum to 1. Okay, so I always need z. That's why we have a z in the denominator of Boltzmann distribution. And as you see, Boltzmann distribution is also an exponential distribution, right? E to the power of minus beta ex. And z here is what? Can you tell me? Is summation of all of the possible numerators. So exactly what we have here, like what we have in these cases. Z is a summation of them over all possible states of x. All possible states of x. What do I mean possible states of x? Assume I have 3 particles, x1, x2, x3. How many cases do I have? 2 for this, 2 for this, 2 for this. 2 times 2 times 2. 8 cases, right? How many combinations of spins can I have? So sum over all of them, right? And I have e to the power of minus beta ex. And This, by the way, this Z in a statistical physics is called partition function. Naming is not important. You can call it normalization factor, right? So we had this probability. The coefficient beta, by the way, you might be wondering, how is it related to meteoristic optimization? I will tell you. Soon you'll see. The coefficient beta is greater than or equal to 0. Defined as this. Beta is 1 over k beta times t. Therefore, it's proportional to 1 over t. What is t? First off, t is the absolute thermodynamic temperature in kelvins. You know what? You know temperature. Temperature is not always in Celsius. We usually say it in Celsius, but in physics, they usually call it in kelvins, right? And when you call it in kelvins, it cannot become negative. It's always greater than or equal to 0. So 1 beta is proportional to 1 over t. And k beta is called Boltzmann constant. Okay. So I defined beta. Now let's analyze it. And now you will enjoy it part by part. If the temperature tends to absolute 0, goes to 0, limits t to 0, what happens in this? Beta goes to infinity, right? Do you agree? Beta goes to infinity. If beta goes to infinity, what happens to P of x? Beta goes to infinity, P of x goes to 0. Do you agree? E to the minus infinity becomes 0. So what does this mean? P of x was a probability, right? Therefore, it means that for absolute 0 temperature, the probability is very low. Therefore, in the universe, absolute 0 temperature occurs extremely rarely in the universe. You can almost never find absolute 0, maybe between galaxies, right? You understand? Okay. Now recall equations 10 and 2. I have repeated them here. The free energy is defined as this. F of beta is minus 1 over beta, natural logarithm of z. The internal energy is, I'm just defining them, right? This is internal energy. U of beta is derivative of beta, F beta with respect to beta. Now, I replace this here. I will get this. That I use the formula for derivative of logarithm. I will get this. Then, according to equation 2, which is this, that is derivative of this z with respect to beta. It becomes this, right? I have brought this z inside. Interestingly, this thing is P of x. Okay, therefore U of beta is summation of Px Ex. By the way, you are aware that you shouldn't memorize anything. Right? Just try to understand. Okay. Now I have P of x, F of beta, and U of U beta. By the way, I could simply say this is a Boltzmann distribution and tell you what is simulated annealing. I want you to understand Boltzmann distribution. Right? So P of x, F of beta, and U of beta. Now the entropy is defined as this. This is definition of entropy. Minus P of x, logarithm of P of x, right? Over all possible x's. According to equation 10, which is this, if I put this here, I will get this term, right? Just take the logarithm of this term. You will get this. Then I can say apply this summation to the terms, right? So I have summation of the first term, then summation of the second term. The logarithm of z does not depend on x, so it can come out of the summation. What is this? This is interestingly F beta, right? And what is this? Summation of P of X. Can you tell me? It's 1. Do you agree? Summation of all of the probabilities is 1. So I will have this plus ln of z, which is according to this formula. Sorry, according to this formula, it becomes minus beta f beta. So we could simplify this equation into this, equation 7. Now, lemma. Don't worry, it's nothing complicated. By the way, I never ask you for proofs. Okay? Never ask you for proof. I tell you the proofs for you to understand. Guys, a physical system. I assume that you enjoy this because you're mostly mechanical engineers, right? Mechatronics engineers. So I think I love this. You love this. A physical system prefers to be in low energy. Hence, the system always loses energy to have less energy. Do you agree? What I'm telling you justifies why simulated annealing works. A physical system prefers to be in low energy. Hence, the system always loses energy to have less energy. Proof. On the one hand, according to the second law of thermodynamics, entropy of a physical system always increases by passing time. So entropy always increases. Entropy is a measure of randomness and disorder, right? On the other hand, when a system loses energy to its surrounding, it becomes less ordered, right? When it loses energy, it becomes less ordered. Hence, according to these two, by passing time, the energy of a system decreases to have more entropy, right? The energy must decrease, so its entropy goes up. According to these two. If you combine these two, you will get the third sentence. Now, corollary. What do I mean by corollary? Conclusion. According to equation 10, which I am repeating it here, and lemma, in this lemma, the probability Px of states in a system tend to increase by passing time. Why? What did the lemma say? E of x decreases. Energy always decreases, right? When energy decreases, this P of x goes up, right? Decrease E of x to 0. What happens? E to the power of 0 becomes 1. If E of x is huge, like infinite, E to the minus infinite becomes 0. So when you decrease E of x, P of x goes up. Therefore, the probability of the states increase. Now, do you understand why it converges? Why the states converge? Because their probability is increasing. Because their energy is decreasing. Right? Okay. So systems tend to become more probable. This idea, this simple idea, is used in simulated annealing, where the temperature of system is cooled down gradually. So first, we start with high temperature. Gradually, we decrease the temperature. It's related to high energy physics. Okay. So simulated annealing is a meta-heuristic optimization algorithm in which a temperature parameter controls the amount of global search versus local search. I will discuss it in a few slides. Okay. So the amount of temperature tells you how much you want to explore versus exploit. It reduces the temperature gradually to decrease exploration. So initially, my temperature is high, I explore more. Gradually, I decrease the temperature, so I explore less and exploit more. Usually, most often, most of the meta-heuristic optimization algorithms first explore, then gradually they exploit. Even deep learning does that. Because in deep learning, you have the learning rate, adaptive learning rate. Your learning rate is huge first. You jump. Gradually, you decrease your learning rate because you want to exploit there more. Right? So recall these two equations, 10 and 3, I'm repeating them. Therefore, the probability mass function of the Boltzmann distribution or Gibbs distribution can be written as this. So what I'm restating the Boltzmann distribution, which was this, using the equation of beta. So replace beta here. Then I can have the Boltzmann distribution as this: e to the power minus ex over t, temperature, the whole thing over z, right? Ex is the energy of variable x, t is the Kelvin temperature, z is the normalization constant. And we can replace this energy with delta E, with the difference of energies. I tell you what, with the difference. So rather than E of x, I say delta E. Delta E, I mean the difference of energies. So far clear? No? Which part? Tell me. You can also ask for clarification more in Piazza if you want. So what did I do? I started with Boltzmann distribution. Then I tried to justify this statistical physics and simulated annealing, because simulated annealing is based on statistical physics and high energy physics. And then I'm going to start the simulated annealing, but there is no time. Okay, so we can continue this the next session, but so far we understood how simulated annealing works, right? Okay, next session we will continue the simulated annealing, and then guys, it's not over yet. We will, so this is the agenda. So we'll continue with simulated annealing, then we will go with a particle storm optimization, genetic algorithms, and Nelder-Mead simplex algorithm. Nelder-Mead simplex algorithm is what we have in F in search of MATLAB, right? So we'll cover important materialistic optimization algorithms. Okay, thank you very much.